Hello students, welcome back. In 6.2, we studied trigonometry of right triangles. Now in 6.5 and 6.6, our topic is the trigonometry of arbitrary triangles. Needless to say, this is an extension. And of course, another thing that you must remember is that these two sections are highly geometric, so please prepare to draw a lot. Let's have a brief recap of what we have been doing. In 6.1, we studied the angle and measurement, especially we talked about radian measure. And in 6.2, we studied trigonometric ratios of acute angles. Consequently, we could inscribe those inside a right triangles, and then we did some geometry of right triangles there. In 6.3, we went beyond the acute angles, and then we considered arbitrary angles. Now the trigonometric ratios were extended into trigonometric functions, which are defined in entire real number system, except for some singularities with vertical asymptotes here and there, of course. And then consequently, we were able to use some techniques of function theory, and one of that was inverse function theory and their domains and ranges and things like those. That was covered in 6.4 when we studied inverse trigonometry and some trig equations too. Now we are coming back to geometry and we are studying triangles again. Let's have a little bit more intense recap. Here we go. Well, let's begin with an equation of a circle. X squared plus y squared is equal to r squared. That's an equation of a circle, circle with radius r centered at the origin 0, 0. As you can see, we can inscribe a right triangle, and consequently, we have Pythagorean theorem. So horizontal squared plus vertical squared is hypotenuse squared, and hypotenuse is the radius. So we have x squared plus y squared equals r squared. Now, does it matter x or y are negative? Well, in this particular case, y is negative. Doesn't matter because we are taking squared and making everything positive anyway. Now, how did they define the radian measure of the angle? Here's a visualization. We define the radian measure of the angle as a counterclockwise arc length from the starting point r, 0 to the terminal point x, y over the radius r. In this case, we are looking at two different radii, but the angle is the same as long as those two terminal points are aligned in the same terminal ray. If we move clockwise, then the angle is negative. Pretty much the same as the number line. If you move to the right, that's positive direction, but if you move to the left, then that's negative. And ignoring the sign, of course, we get this. Theta, the radian measure of the angle, was defined by arc length of the radius, counterclockwise arc length, to tell the truth, but throw away the direction, then we just have arc length over the radius, so arc length can be calculated as r times theta. Here's the arc length formula. Okay, that was an application in geometry. And let me remind you of the definitions of the trigonometric functions. And let's see, we're going to have something in first quadrant soon enough. Looks like okay, I got it. Okay, and in this case, trigonometric functions are the same as trig ratios. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Y over r, x over r, y over x respectively. And cosecant, secant, and cotangent are their reciprocals respectively. Now what if we go beyond the acute angles, kind of like this in third quadrant? Now the angle cannot be inscribed inside a right triangle, but we can still utilize right triangle, as you can see in this kind of picture. But in any case, we cannot use the terms for right triangles like opposite or adjacent to hypotenuse. We have to call x and y as horizontal and vertical, and r is just the radius of this entire circle, not the hypotenuse. In any case, we still have the same definition, same identities, same everything. Now, here's a couple of applications in geometry, area formulae. An area of a sector can be calculated like this. Area of the entire circle is pi r squared. And we want not entire disk, but only the portion given by the sector. And the entire angle is 2 pi, and the angle we are interested in, highlighted part, is theta. So multiply the ratio of theta over 2 pi. After a little bit of simplification, we have 1/2 r squared theta. That's the area formula of a sector. How about triangle? Here it is, 1/2 AB sine of theta. And we can, let's see, I'd like to have acute angle case first. It's easier to understand. Okay, here. We can write the area formula of a triangle as 1/2 AH. A is base length and H is height. But height can be calculated from trigonometry. H is B sine of theta. The reason is because if you look at the left-hand side triangle, then B is hypotenuse, so H over B is sine of theta. So H is B sine of theta, plug that in. Then we have area formula, 1/2 AB sine of theta. Now, does it stand true for obtuse triangles? The answer is yes. Well, in this case, just do not consider this small a part. Just consider this b part as a radius, and we have an angle theta that goes beyond pi over 2, and the terminal point is a second quadrant. But still, h is vertical and b is in this case radius. So h of b is sine of theta, and consequently, h is b sine of theta. That remains true. So we have the same formula in the end. Okay, we don't have time to, well, I think we still do have, we have enough time, so let's discuss some applications of right angle trigonometry with some very, very simple examples. And here's one, finding out height of a tree using a triangle. Please note that we can form a right triangle from the tip of the tree and tip of the shadow and then the base of the tree. And the right triangle has one angle 25.7 degrees, and adjacent side, the horizontal is 532 feet. Height is unknown, but we can find out using a trigonometric function, tangent function in this particular case. Here's another example. This time we have two right triangles, but in any case the key was right triangle. If you look at the outer shape, then it looks like an arbitrary triangle, arbitrary acute triangle, but if you decompose it into two right triangles and apply trigonometry separately, you can find out the distance between the observer and the flagpole, the x value. And here's the color coding basically. The blue portion, the top portion, the red portion, bottom portion, those are both right triangles. So we were able to use right angle trigonometry, and was kind of like this: a plus b, and let's go back to this picture. A plus b is height of the flagpole, 60, and then what is a? We can figure it out from this trigonometry tangent function. What is b? We can figure it out from the trigonometry again, and if you manipulate, then we end up with an equation of x only, as I highlighted. So you can solve it and punch in the calculator to figure out everything in the end. But then again, what if we have arbitrary triangle, not right triangle? In that case, what kind of tools do we have? Well, in this introductory video, we're going to introduce two typical techniques. One is the law of sines, and it is stated like this. First, we start with a triangle ABC. where capital A, capital B, and capital C represent the size of the internal angles. Capitals are internal angles, and most of the time when we use capital Roman, we are talking about degree angles. And if we use Greek letters, alpha, beta, gamma, things like those, then those are usually radian angles. But you don't really have to follow that convention. For law of sines, it is traditional to follow this convention. Capital A, capital B, capital C are the internal angles, typically in degree measure. Now, small a, small b, and small c are the lengths of the sides, but there's a rule. We must select small a, small b, and small c as the opposite angles of those capital A, capital B, capital C. And I did even color coding in this picture. And this law of sines applies not just for acute triangles, but obtuse triangles as well. As a matter of fact, this is arbitrary. No matter what triangle I just get, this program is randomized, so you will get all kind of triangles. It doesn't matter, this rule stays the same. And we can use that to create an equation or a number of equations to identify some unknown values from known values. The typical cases are kind of like these, where we have all three angles and one side. Actually, in this particular problem, I gave you only two angles, 20 degrees and 25 degrees, but the third angle you can easily find out because some of the internal angles of a triangle is 180 degrees. So subtract 25 and 20 from 180 degrees, you have 135 degrees. So easily you can find out all three angles. And on one side, you can find out the other side. Some other cases are possible, but those are rather unusual and a little bit harder. We're going to consider those kind of things a bit later in the next video. Now, let's move on to the other topic that we have to consider, the law of cosines. And it kind of goes like this. Here's a summary. And again, that goes to the same kind of picture. Excuse me, the picture is a bit too big. I want it small enough so that I can see it in the same viewing window. Oh, come on. Okay, that's good. Arbitrary triangle is given, and again the same convention. Capital A, capital B, and capital C represent the size of the internal angles, typically in degree measures, traditionally. Small a, small b, and small c are the lengths of the opposite sides. And a squared, small a squared, is equal to small b squared plus small c squared minus 2bc cosine of a. And then similar rule applies for the angle b and angle c as well. And those three are called the law of cosines. Let's make one more observation here. In a special case, say for example, in a special case, when c is 90 degrees, for example, in that case what? What is cosine of 90 degrees? Or cosine of pi over 2? That's 0. So this highlighted part, this blue part is 0. So this entire part is 0. So what do we get? C squared is equal to a squared plus b squared. That's the same as Pythagorean theorem. For right triangle, yes, it works. It's an extension of Pythagorean theorem. For arbitrary angle, we have the law of cosines. So you can regard the law of cosines as a natural extension of the Pythagorean theorem. Let's see, we have another application here which is not really discussed in our textbook, so I kind of de-emphasize in gray. If we have time, we'll go over these. One final application is this. Law of cosines can be used to determine triangles when three sides are given. So why don't we discuss an area formula when the three sides are given? Well, here it is. S is half of the perimeter, then area can be calculated by this formula, and this is called Heron's formula.